I'm talking about end-to-end annotator bias approximation on crowdsourced single label sentiment analysis. And here is our research overview. So we talk about crowdsourcing, and in crowdsourcing we have annotators, so many crowdsourcing annotators, and every crowdsourcing annotator has its bias. And we want to model all these respective biases from the annotators, and we want to model each annotator separately, such that we can remove the bias from each annotator and estimate an according ground truth. And this one we want to do for the tasks of sentiment analysis, which come in a single labeled fashion. And we want to leverage state-of-the-art methods such as artificial neural networks and end-to-end learning. So I want to give you a brief introduction to our terminology. So crowdsourcing, in our case, it's about crowdsourcing annotations. This means to collect annotations from many non-expert people, from many amateurs. And many amateurs means that many people, for example, here they have an image labeling task. Many people are labeling images. Here's an example where a dog is shown on an image, and most of the people are giving the correct labeling, but there are some people, some subjects who give wrong labels, who recognize the dog to be a cat, either because they are inexperienced or because they might have questionable motives, or also they don't pay attention to what they see and thus they label differently. And what then happens is there's an annotator bias coming into place. So, for example, for that devilish annotator here, it might happen that this annotator keeps annotating dogs as being cats, and thus there will be an overall bias towards cats because he's always recognizing cats everywhere. And that can lead to a very strong machine learning bias too. And these are the terms of crowdsourcing and annotator bias, and this is what we want to work on. And then there's also the term of ground truth, which is how do we get rid of the bad annotations and find a good smallest common denominator. This is, for example, can be done, for example, by majority voting. So we take the majority annotations, and just see which is the most voted, most given annotation, and that's the one that we take. That's the naive way of finding a common ground truth of everything. But then still there are the separate annotator biases. So which are the ways how we can resolve that? So there's one traditional way, which is the way which we see at the top here. The traditional way says that we have the texts in the case of NLP. So we have text that we pre-process. We derive features from these texts. We count the words, for example, and these are the features that we have. And on the other hand, we have the crowd annotations from which we derive a ground truth using majority voting. And then we have a ground truth, we have the features, we train a model, and that's then the classifier that we have as an output. And we want to introduce an alternative, which is end-to-end learning, which means that we provide texts in addition to crowd annotations. And we apply a learning algorithm, which gives us everything, which gives us the classifier, which gives us the features, the ground truth, and the annotator biases all in one package, such that we do not need to do any of these pre-processing steps. So it should resolve the crowdsourcing task completely from A to Z. And how do we want to achieve that? So in a nutshell, we have the text, we have a kind of black box model that I will explain it later on, and the model has as output probabilities, which help with the classification. For a sentiment, that could be two outputs, which is positive and negative, positive sentiment and negative sentiment, and for both, there are respective probabilities that it's positive or negative. And then, because we want to model each annotator separately, we do it in a multitask fashion that for each annotator, we have a separate matrix, which is a 2x2 matrix for sentiment analysis, which is multiplied by the probability outputs. And then for each annotator, we get a respective classification separately, which tries to mimic the biases from each annotator. So each annotator is modeled here with these annotation heads or bias matrices, as we call it. And these really encode also the biases from each annotator, how they deviate from the latent truth, which we call this probability layer here. And I will not go into detail about the classification internals, but it's essentially just the weighted average of word vectors, whereas the weights of the average are determined by attention weights, which are trained separately. So the most important thing is really we have here for each annotator a separate loss and a separate annotator bias matrix, and that's modeled independently of each other. So what we see is we have the bias matrices, which are these T matrices here at the bottom, and at the top we have the confusion matrix, which is the mismatch between the latent truth and the actual annotator annotations. And what we see is between the biases and the confusion matrix, there's a big mismatch in the related work. So there are algorithms which do end-to-end learning, which resolve the problem like this. But the bias matrices do not match the confusion matrix, and we are providing a technique which makes the bias matrix becoming the confusion matrix and then being trained and being found in an end-to-end learning scheme. And that's the actual contribution, that we resolve that mismatch that is there in the literature between bias matrices and confusion matrix, such that the annotator biases are modeled actually correctly, which is not the case yet. And how do we do that? That's essentially, if we reduce it to the most important step, it's just that single thing. So there's the cross entropy loss, which is defined like that. As the cross entropy loss is defined as that formula which we see here. It's just essentially the sum of all the logarithms of the probabilities multiplied with the actual labels. And if we remove the logarithm from the whole formula, then this leads to an outcome which probably makes these two matrices converge to each other during the training process, which is then correctly end-to-end learned annotator bias. Yeah. So and why is that? So if you remove the logarithm from here, essentially you remove the fact that the logarithm creates a high loss for false negatives. So because of this formula, it is the negatives, the false negatives create a very high loss, and the logarithm improves that. The logarithm increases that effect. And if we have a annotator who's giving many wrong annotations, which is a spammer annotator, this person will create a lot of loss, like much more loss than other annotators, and it's much more considered for the overall machine learning training, and that distorts not only the ground truth, but it also distorts the overall training, and it also distorts the classification. That affects also the classification from the other annotators by that ground truth from that latent truth layer, which is shared also. And that's basically something that leads to many problems. And here we have our first experiment. This essentially, these are confusion and bias matrices. So it's the other way around, and at the top there are the bias matrices, and the bottom are the confusion matrices. These are trained on gendered sentiment data set. So there's a split of female and male sentiment annotations on the data set. It's taken from the literature. And what we do is we train the model on these things, and we have for male and female separately an annotator bias set. We train that model, and we want to see if the bias matrix from our model matches the confusion matrix. And this is then dependent on which loss function we use. If the loss function in the end has a logarithm or doesn't have a logarithm. So here it does not have the logarithm, here it has a logarithm. Here it does not have the logarithm, here it has a logarithm. And what we see is where it has the logarithm, there's a mismatch between the both matrices at the top and bottom. And where we do not have the logarithm, which is here, there's no mismatch. And the same is also happening here. here is no mismatch, and here is a mismatch. And this basically shows that our approach of leaving the logarithm away is working, and by just giving a good approximation of the actual annotator biases. And this works even well if you include 80% random annotations for males only. The second experiment is we have a ground truth estimation on single-labeled crowdsourcing set, which is our data set. So there's only one annotation for each sample. And the good thing about our model is that you can train our model on that kind of data, even though there's only one annotation for each sample, which is rather unusual, I would say, which is an advantage of the end-to-end learning scheme. And what we basically see is that our ATNet approach is very close to other ground truth finding methods, such as David-Skeen, and another base model, which is just trained irrespectively of all the annotations. So we have a very high iterator reliability, iterator agreement of these three models, which show that the outcome in the end is eventually similar, if not more or less identical, which means that there's nothing unconventional to happen when we apply our model. So it's everything is working as expected, basically. There's no outliers or unexpected effects happening if we use our modern approach here. And then there's a third experiment where we just do a straightforward sentiment classification on 3 data sets, which is once the general TripAdvisor data set, which you saw initially, our own organic data set, which is singly labeled, and an emotion data set, which is from the literature also. It's from a Matrices paper. And what you see basically is that our ATNet approach has a relatively good performance for classification with respect to one score and accuracy. If you want to classify the sentiments, I wouldn't say that it's specifically better than like when you remove the log compared to when you have the logarithm, but it's definitely better than if you train irrespectively. Like if you don't train based on the annotator specific information, if you leave the annotator specific information out, if you don't model the biases, the model becomes worse actually, which is the base model here. So the base model is worse everywhere, significantly worse. So modeling the annotator biases makes a lot of sense, and it's something that's very easy to do, and something that we would generally recommend also. The logarithm removal does not give so much benefit here. So in a summary, you can do ground truth estimations even in singly labeled crowdsourcing setting, and the ATNet gives noise robust and consistent results. The annotator biases are modeled precisely and correctly, which is basically something that we add to the literature here. And then we also see that the classification does not so much benefit. However, annotator bias modeling is helpful. And here I want to say thank you very much, and I would be happy if I have some questions that I could answer. Thank you.